Okay, so good morning. So here I'll just try to provide a very high-level overview of where we stand on the MVAPICH project, the latest status, and some of the future roadmap. So as many of you might be experiencing, I mean, just take a look at the history. Like 1975, we started with broad scientific computing HPC. After 25 years, big data analytics came, and then after 10 years, the AI came. So with that kind of a background, nowadays, any kind of a modern workflow, you try to take a look, it is not just HPC, but it also has AI and big data. And Sadaf's talk also indicated that. So in this kind of a context, the question is, as we are deploying these large-scale systems, not only we just need to address the HPC issues, but we also have to address the AI issues and the big data issues. And we need that kind of a distributed runtime, which will provide scale up and scale out, whether you call CPU, GPU, any kind of interconnect. So this is where over the last few years in the MVAPICH group, we are trying to expand or diversify our scope. So not only just traditionally focusing on the HPC, but saying that, okay, can MPI-driven converged middleware be designed and address all these three domains? So in that context, I have a very small issues here. I'll start with a very brief overview of the MVAPICH project. And especially since last 2 years, we have been hearing a lot of feedback from you. So we have created a new series called MVAPICH Plus. Okay, I'll go into a little bit more details on that, what that means. And then I'll go into a little bit details like MVAPICH Plus, that's the latest 4.0B. We released on Sunday night. If you are on our mailing list, you would have seen that. I'll try to show you some sample numbers that I've indicated some numbers on our system. So we have started taking numbers on other systems. And while we are continuing with the MVAPICH Plus, we are also getting engaged with Broadcom. We have an optimized version, the 2.3 series. They have a Rocky adapter. So I'll try to show you how we have optimized there. And of course, the cloud is expanding. We have also working on the optimized version for the cloud, Azure and AWS. And then I'll go into this converged software stack, how we are trying to bring like the AI, the machine learning, the deep learning, the Spark, big data, everything. I'll try to show you some numbers. Then OSU micro benchmarks, some of the latest developments. We also have the project InfiniBand network analysis and monitoring. And as we go through these, we are also, as we interact with users, we try to bring a lot of knowledge. And we also have an application best practice kind of focus. So we try to provide all those results on our website so that the other people can use it. And then some of these upcoming features, I'll go into more details. Like we support AMD GPUs as of now, in addition to NVIDIA. But there is this new mechanism called on-the-fly compression. It is available on the NVIDIA GPU, but not in the AMD GPU. That will be coming next. And then Intel GPUs, that is the next stage we are working on. We have some initial solutions on the 4.0B, but I'll try to show you some of the things in the pipeline. And then we are also expanding into FPGA. So I'll try to show you some of the MVAPICH FPGA and OMB numbers. And CXL, I was hinting in the introductory remarks, that is the next direction which is coming. Hardware is coming. The hardwares are not public out there, but we have started like doing the emulation and introducing OSU micro benchmark for CXL. And I'll try to show you some of the initial numbers. And in the AI context, I think yesterday you heard the presentation from Quentin. So in addition to the training, fine-tuning, we are also expanding onto the inferencing, and that's also inferencing very high resolution images. Okay, that is a kind of the focus. And the other project which is emerging is the trying to come up with all these things through a conversational AI interface. Okay, we'll talk about that, and then we'll conclude. So this is the very high-level overview. Many of you would have seen this slide. If you go back like 24 years, we started this project in almost October 2000 when InfiniBand standard was introduced. Prior to that, in my group, we were working on MirrorNet, Quadrix. I think some of you might be remembering those old proprietary networks. So when InfiniBand came, hardware was there, but nobody knew how to use it on a real system. So we're the very first group in the world jumped into that, and we had the first MVAPICH open source released at the supercomputing O2 in Baltimore. If some of you were there at that time, almost 22 years back. And I can remember like putting together an 8-node system with InfiniBand was challenging. During the show floor, things were crashing, okay? But now you can see over the 20 years, what has happened. Systems like Dan is sitting here deploying 8,000 node InfiniBand clusters and all in a very easy manner. And I'm very proud of my team. We have been a part of this ecosystem for the last 24 years. And in addition to InfiniBand, we have expanded to all the different interconnects. Now you name any HPC interconnect, we have the solution. More than like 3,400 organizations, these are the registered organizations in 92 countries are using it. And just this month, we have crossed 1.81 million downloads from our website. We are a part of all other stacks like OpenHPC, Red Hat, SUSE, SPAC. We don't keep track of these, but these are the direct downloads from our website. And of course, we have been empowering a lot of top 500 clusters. We are hearing some of these things. Dan will be talking also much more detail in his keynote talk tomorrow. So you can see here very rapid rise of the download count over the years. So if you go into the architecture, so this is how we have architected. Left-hand side, you will see all the networking technologies. Every time a new networking technologies or a version comes, its features and all, that becomes the food for thought of our group, saying how do we exploit that feature. And then, of course, the right-hand side is all the CPU, GPU, DPU kind of thing. The middle one is our actual research. So this is where first we jump in and try to come up with the papers. We publish those papers. And over the years, we started with MPI, linking all these things, and gradually we expanded to PGAS, hybrid MPI, PGAS. There were some time, these were very high important topics. Gradually, that interest in the PGAS has gone down. But then we have expanded into the deep learning, big data, data science. So that's how the overall architecture looks like. So our primary focus, because we are in academia, our primary focus is publications. But then we also have a very rigorous QA procedure. As you can see, like we have very in-depth test suites. We have many software engineers in my group. We almost like spend about 18,000 core hours per commit, okay, to go through all the different tests and all. And over the years or months, we try to strengthen that QA release. And then we also not only do like a micro benchmark level, we do some application level, and then we make the release so that you can actually download and then use it. So all the versions, even like a alpha, beta, RC1, RC2, we go through testing. So let me go into this MVAPICH Plus series, and it will give you a little bit of history also what has happened. I don't know how many of you have used MVAPICH 1. Yeah, okay. Several of you, okay. So that was the MVAPICH 1 when we started in 2002. That was the first version. We continued. It started with the basic InfiniBand support. And many of you don't know the MVAPICH acronym, how we came up with that. First it was an MVAPICH derivative. The first verse level implementation from Mellanox, if you remember, MVAPI, it used to be called verse level API. And then prior to InfiniBand, if some of you remember, there was a MVAPICH, MVAPICH, from I think NERSC kind of thing. So all these things, we wanted to give credits to all of them. So that's how this MVAPICH term was coined. So we started with verse. So that was the IB, and then gradually, Open Fabrics ecosystem came. IB and iWork got merged, so we supported iWork. Then Omnipath came with their PSM. So that's how we were supporting, like almost 2002 to 2010. So then gradually the MPI standard that was the MPI standard 1, then MPI standard 2 came with one-sided support and all. So we started with 2004, this new series, MVAPICH 2, and then that is still continuing, and then gradually we expanded not only to other systems here, Rocky, iWork, the AWS EFA, OPX, Rockport, and then also the GPU. We did the GPU Direct RDMA together with Mellanox and NVIDIA at that time. We came up with this solution. So this series is continuing. But then if you remember here, what happened, we had multiple versions, MVAPICH 2, MVAPICH 2 GDR, MVAPICH 2 X, MVAPICH 2 AWS. And in previous mug, actually we got feedback from people saying, look, this is becoming very complex. There are so many different versions. Of course, every version, like the time to market kind of thing, we were very quickly to bring out those solutions. But then gradually we saw that there are so many versions. So based on that request, people suggested saying, okay, why don't we all combine this? And this is where the MVAPICH Plus comes in. So the MVAPICH Plus, basically, it tries to bring all these things with one stack for all architecture and interfaces. And so then at the same time, the field, you saw that I was telling HPC came, but then of course the newer workloads are coming, AI and big data. So then we said, okay, let's see how that MVAPICH Plus can be again modified to handle all these things. Now, interestingly, if you see, of course, all of these workload need scaling and performance portability. Okay, I jokingly say nobody wants LPC, low performance computing. Nobody wants, at least in this room. Okay, everybody wants HPC, and we have to give the performance and the scalability. The larger is always the better kind of things. But at the same time, if you take a look, designing these MPI libraries or any communication stack, not only MPI, the same thing is happening with TensorFlow, PyTorch, Spark. There are so many combinations. Okay, if you take a very quick look here, like there are in the market, there are 3 CPU types now: Intel x86, AMD x86, and the ARM. 4 different interconnects. The common one, InfiniBand, Omnipath, Rocky, and let's say Slingshot. Just 4. There are others. GPUs, there are 3: AMD, Intel, and NVIDIA. So if you do a quick math itself, there are 36 combinations. So any stack you do, you have to take care that performance on 36 combinations. Okay, and each one of you, I mean, many of you in the room, deploy all combinations. All right, from as the vendors bring, give you discounts or based on your overall thing. So as like an MPI library provider, we have to actually take care of all these 36 combinations, and that to the best performance. Okay, so since we do that for HPC, then the question is, okay, do you really want to repeat that for AI and big data, or I can leverage? So that's what is the motivation of the MVAPICH Plus, that it is a converged software stack, and not only we can provide this on premise, also we can provide it on the cloud. So this is where we are diversifying. I want to show, like at 2022, we started this MVAPICH 3 and MVAPICH Plus 3.0. So what we did, all these things, the ecosystem, as some of you know, it was the open fabrics, but over the years, the open fabrics community has diversified. They have divided. Actually, one is the UCX community and then the OAFI community. UCX community is being led by NVIDIA/Mellanox. OAFI community is being led by Intel. And especially the interconnect Slingshot, which came into the market, and that didn't have any verb support or anything. It was only provided through OAFI. Okay, so that actually was also a big motivation for us to move into this direction, so that we provide UCX and OAFI, and through that we can actually provide all interconnect, okay, especially internal. But then what happened is, we had our original designs. If you are familiar with some of the code, MVAPICH, we had our native verse level support. Okay, and through that we had a lot of architecture detection, tuning, all those things. Over the years, we had optimized for all the machines. We lost that in that series because we just provided UCX and OAFI support. So in the internode, you either go through UCX or OAFI, but then we lost all our intelligence out there. And that has led to this MVAPICH Plus 4. Okay, so MVAPICH Plus 4 now not only has the UCX and OAFI, but we have bring back that verse level support, so that we can have our intelligent architecture detection, tuning tables, all those things. So this is where we want to really focus on as we move forward, and that is like a converged software stack. Not only it will try to target the HPC, but all other workload. And at this time, we are still keeping here. These have not been phased out. Of course, that has been deprecated many years back, 2010. We deprecated. People are still using. Might be another 1 or 2 years, but gradually we'll move to this 4.0. And that also has the MPI 4 standard, 4.1 standard. So we are compliant with the very latest MPI standard on all the interconnects, all our intelligence. So everything is focus is going on to that. Okay, so I just wanted to give this picture so that everybody understands what is happening. So with this, now let's go this. This is the latest MVAPICH Plus 4.0 B release we made on Sunday, and it supports all the features MPI 4.1 standard. And this is actually combines that MVAPICH to GDR, MVAPICH to X, MVAPICH to AWS. So we want the community to move into this version, okay, which is a superset version. And this is what it supports both OFI, UCX, including our burst level support. And these are all the combinations. I talked major CPUs, GPUs, HPC internet. The 36 combinations we are trying to support through this. Everything is not optimized yet because we brought our new logic, and you will see by the time we go into the RC1, a lot of these systems will get optimized, and that's what you will see. And in addition, we have this new thing we have been working on for some time called on-the-fly compression. These are for the GPUs. Especially trying to utilize the GPU cycles during communication. Of course, people have been using GPU for computation, but for communicating large messages, we try to compress using GPU cores and then send it so that the message size gets reduced. You get improvement in bandwidth, and the other side we do the decompression, even though there is an overhead, but many times we win. I'll try to show you some numbers. And then, of course, through that, we are able to support all these things. So I'll try to show you some initial numbers. So here I'll try to show two systems. What we have done some initial evaluations. This is the first one is AMD CPU, AMD GPU, and Slingshot. See, this is like a frontier at Oak Ridge or Tioga, Livermore. So I'll show you some CPU-based, GPU-based. The other one is Sadaf's machine. Thanks her for providing us access. Grace, which is the ARM CPU, Upper NVIDIA GPU, and Slingshot, GPU-based. And the third one, we just got access, Dan's machine, that is the Vista system which is coming. We are just running some experiments. Those numbers are not there yet. So if you see here, so this is the Slingshot Frontier system, and we are comparing the default library is Cray MPICH there. Okay, that is the Cray system. But as you can see, we are able to beat Cray MPICH in a big manner in terms of the latency. These are the kind of the intranode. We have our own designs, and that is where we see a lot of benefits. On the internode, we are comparable to pitch because again the underlying the same UCX, OFI we are using. So it's there, and with our new design, we might be able to improve. We have not done all optimization and tuning, but at this time at least it is same on the internode and the internode. So these are the CPU based. And the collectives, again, as you can see, like since we have very good intranode design, when you go for a collectives, it is a combination of internode and intranode, so we are able to give better performance compared to Cray MPICH. On the GPU side, so this is again the Cray MPICH, and we are comparing with MVAPICH Plus 4.0. We are little bit, as you can see, the latency, there is a little bit of trade-off for small messages. We are able to do equivalent. So this is actually on Tioga system. This is a MI250X GPU at the Lawrence Livermore, and here you see the GPU on the bandwidth wise. We are able to give better performance, at least for the medium and then small messages, large messages. We are more or less same. And in the internode side, here also I think as you can see, like we are able to give benefit in the small and medium message size. And then the collectives is actually our strength. We have been working on all different algorithms over last 20 years. We have a lot of algorithms. So always the end thing is that whether we get access to that system. Once we get access to that system, we know how to try all the different algorithms and put appropriate tuning points. So as you can see, this is on the all-to-all. We are able to, compared to Cray MPICH, we are able to beat by 50% kind of thing. So this is the Sadaf's system. See, indicated some slides. Again, these are some initial numbers. We are still talking with her team whether we are using the right configurations and all. Excuse me. So this is the GPU optimized. So here you can see like the red line. This is where we have the GDR numbers. She reported 3.7 microsecond. We can actually send data from GPU to GPU. And especially small and medium messages. Large, we are more or less the same. And These are also the similar like on the internode side, we are very similar because we are just using the Cray OFI there. But collectives here, we have just started very small systems, node configuration, all gather like a 48% benefit, all to all is 33%. And of course, the system is very heavily loaded. So always happens like we are trying to, if somebody can give us their system for few days, it is a dream for our team. Okay, we can run all experiments and tune all those things and give you a very nice thing, but it doesn't happen because there's so much competition for resources, kind of things. But unless you get, I mean, there is no theoretical model here, or there is no broad models are there. We have done that design, but you have to be on the system to run all those experiments and see where the trade-off lies. There are so many parameters within the MPI library, and then that helps us to, on real system, we can actually get to good performance. This is actually all reduced on one node. Again, on the MVAPICH system, so as you can see, compared to Cray MVAPICH, we can actually beat by 74% kind of things. So these are the micro benchmarks, and we need to really run applications and both AI, big data, all those applications, HPC applications, to see how much we can push the capabilities of those applications with the new designs. So as we are going into the 4.0B, so this is the project we have been working with Broadcom. They have funded us for last few years. So as you know, the ROCE, Broadcom has its own ROCE. ROCE is for RDMA over Conversion Enhanced Ethernet. The InfiniBand, like Mellanox, NVIDIA, they support ROCE, but Broadcom has their own ROCE design. So we are working very closely, and we have enhanced some of the UDRC hybrid protocol, optimized the CPU mapping, asynchronous threading, speed up MPI startup, some coalescing we have done. So here you will see that, so this is the comparison with OpenMPI, because that is a common stack for ROCE. And here you will see like for small message latency, we can give almost 24%. Similarly, MPI already used is 12.4x. MPI scatter is around 5x. We are able to give on that system. And that is the CPU. GPU is also very similar. We can give you like a 53% reduction in the medium message latency, and 2.6x in bandwidth, and 35% reduction in all-to-all latency. So here again, I'd like to say, we are going, I indicated that in the previous slide, we are taking a vendor neutral approach. Okay, I know there are multiple vendors here. I respect everybody, but we are vendor neutral. So we work with all the vendors. Okay, and then based on your capabilities of that system, we can optimize. Okay, so that we can give a vendor neutral stack, and anybody else in the community can use it. And these are actually applications on the Broadcom ROCE cluster. OpenFOAM, as you can see, that is a very common application. This is the motorbike example, and up to 128, like 16 nodes, 128 ppm scale, well, we are able to reduce time by 45%. Okay, at an application level with our design compared to OpenMPI. Same thing we have done for GROMACS. Same thing also for CP2K. Okay, but these kind of things actually we have been working with them for almost 2 years. Okay, to really bring, because we have to understand all their inside things, what they have done in the adapter, and then bring our designs. We do a lot of experimentations, tune, but this is what you see at the end. So similarly, we are working with cloud providers. Cloud providers, as you can see, they are also following the HPC trend, especially Azure is purely InfiniBand, their HPC instances. So over the years, what they have done is, in fact, once we make the release, in the beginning, we are making an Azure release directly from our site, but then gradually they have taken those things and put it into the images. And here we just like recently they had asked us saying, okay, what is the difference between MVAPICH 2 series and 3 series? We did some analysis here. I mean, broadly we give the similar performance. Okay, kind of things. A little bit by bandwidth we are losing there. MVAPICH 3 is giving a better performance there. And on the AWS side, interesting things, as you would have seen, they have an elastic fabric adapter. Okay, that has been there with AWS for many years. So we did a customized design for that. It has some similarity with InfiniBand, but not exactly things. So we did that. But then at that time, we didn't have the Wi-Fi support, okay, or the LibFabric support. But now, since we have the LibFabric support, either you can go through the EFA or you can directly utilize our Wi-Fi. Okay, so both options are available. With our optimized release, so here again we are comparing with our this the Wi-Fi MVAPICH 3 and OpenMPI comparison kind of thing. So we are able to give better latency on the large messages, but we lose in the bandwidth, and we are trying to take a look at optimizing that. And these are the previous series with our native EFA design. So there again, we had the previous MVAPICH to X, remember, and we are trying to bring those designs into the into our MVAPICH Plus. So there you can see directly these are like a weather forecasting WRF code, mini AMR code. We are able to perform the best compared to OpenMPI and the MVAPICH to X default. So those are the kind of the sample numbers. Again, as we get access to more systems with the MVAPICH 4, we'll be able to do more kind of the experimentation and share those numbers. But now let me go into a little bit of the AI workload. So here what we have done, as I motivated, we are trying to use the MPI as the runtime. Okay, so that I know different vendors have like there are different collective communication library. NVIDIA has Nickel, AMD has RICL, Intel is saying XCCL, SCCL. Everybody is using that terminology, but then that only happens for some system. Okay, if you modify all those different combinations, then you lose those optimizations. Okay, whereas MPI libraries have been optimizing the collectives for many years, so we try to leverage that. So what we have done is we have actually released some of these modules. I'll quickly go over that. Through that, I'll try to show you how we are trying to bring different kind of parallelism for training, inferencing, or machine learning. So what we have done here, this is kind of the overall architecture. So many of you might be familiar with Horoword or TOS distributed, DeepSpeed. So these are the middleware for the AI workload. So what we have done, so typically those are linked to the Nickel or RICL, those kind of libraries. So we have linked that to our MVAPICH library. Okay, so that instead of using a Nickel call, you can one can use MPI reduce call or MPI all reduce, MPI all to all, those kind of things. So with that, actually that gives flexibility. And the one thing I would like to indicate that at the top level, we don't do any change. So your application remains unchanged. So if you are using PyTorch, distributed PyTorch, that remains like that. Okay, it's just a lower level, you need to make the changes so that you have the new ecosystem and you can leverage the MPI. So with that, we made this HiDL. We call it high performance deep learning. You can go to this stack, and here you can see like some comparison with Nickel, our MVAPICH to GDR. These are the previous releases, and you can see you can get a boost in the performance. Okay, instead of using the collective libraries, and that actually scales. So these are the numbers like these are a little bit older numbers. When Summit had come, we were able to scale up to like a 1536. This is on TAX, a dance machine. Many people, whenever AI comes, they think GPU is the only one, but you can also use CPUs, especially when you have large scale systems. So here we are able to scale on Frontera, like on a 2000 nodes, okay, 56 per node, 56 cores. So very large scale system, we are able to have CPU based thing. We are able to get like a 206,000 images per second, and you can actually train ResNet 50 in 7 minutes. Okay, so if you have access to very large scale CPU system, you can also use training. And of course, the same framework you can use for GPUs. This is like we scaled it to 1000 voltage GPU. So these are purely MPI driven solution. We are not even touching Nickel or RICL or any of those underlying communication libraries. And then I mentioned about this on the fly compression, and especially this on the fly compression, we brought our collectives, not just for point to point, but also for collectives. So left hand side is trying to show the PSDNS, which is a scientific simulation, but the right hand side is the DeepSpeed. So this is where like Amar will be talking a little bit more later from Microsoft. So there we are able to experiment and the DeepSpeed using all-to-all, and then all-to-all, if you can actually compress, you get a benefit like almost 35% benefit in running your training. And this was available in the MVAPICH to GDR 237. And now we have actually implemented all reduce, because that is the collective, which is very extensively used in the AI workload, and that is actually available in our MVAPICH Plus 4.0b for NVIDIA GPUs. Okay, and we are gradually moving all these things to AMD GPUs. And here again, you can see like a ResNet X, Convolution Next, wide ResNet. Everywhere we are able to give like a 26%, 30% benefit in the training time. Now, interestingly, so while we are running these experiments, so based on the feedback we have seen, yes, of course, you can go through MPI. From an MVAPICH perspective, we focus on that. But if you have some new systems, it may not be all optimized. Okay, like as I said, MPI, all these collectives, it takes some time to optimize. So what we did is like might be on that system, let's say it's a NVIDIA system, Nickel is always optimized, okay, because it's a vendor supplied library or AMD Nickel. At some given number of GPUs, given number of message sizes, might be MPI is not optimized. So to take advantage of both, we initiated this new thing called mix and match runtime. Okay, and it's publicly available. You can go there, and with few lines of code changes at the top level, you can actually run some experiments. And based on those experiments, you can actually say, okay, for this message size, I can use RICL. Let's say it's an AMD. And for this message size, I use MPI. So you can actually do mix and match. So always you try to do better than either MPI or the collective library. So then while we are continuing on the training side, we are also focusing on the inferencing, because that the inferencing is getting more and more prominent these days. So here again, there are a lot of techniques. This is the paper we presented at HiPC 2023, and we have made a release. So this actually, there are a lot of interesting things, different techniques you can use, dynamic batching, concurrent instance, and what we proposed here, something called a temporal fusion. Okay. Now think of the server side, like let's say ChatGPT, you are initiating a request. Okay. All of you would have done ChatGPT, you will see a blink, blink, blink message, am I right? That means the request is going and then the answer is coming. Think of the server side, millions of such requests are coming. So how do you handle that? It is something like a job scheduling problem, which many of you might be familiar. So then the question is on the other side, on the server side, how do I use those GPU systems? How do I launch those kernels? How do I take the request, associate with the model? So we are working at that level. And so here we came up with like this was presented. At that time, the faster transformer was the best. And here we were able to show, compared to what faster transformer was providing, we were able to get almost like a 16 times speed up. Okay? But I believe some of these designs have been taken into the TensorRT recently, and they're also using similar techniques here. So those are the deep learning, the similar things we have done for the machine learning, the traditional machine learning. So here if you see the QML, which is a package which is used for the most of the machine learning, and the traditional approach has been go into that nickel box. So what we did is we added this MPI for pi and MVAPICH to GDR. And if you try to take a look at these k-means, linear regression, nearest neighbors, truncated SVD, these are like the standard machine learning applications, and we are able to give benefits compared to the nickel library, okay, on NVIDIA GPU systems at a 1.35x, 1.6x dynamics. So those are the kind of the machine learning. Then coming to the big data, some of you might be familiar again, we had the MVAPICH project, then we also created a high BD project, like a high performance big data project. So we took like a Hadoop, Spark, and we natively redesigned to the verse level, InfiniBand, okay. But now let's say the Slingshot is coming or Rocky coming. There is no point in redoing all those work. Okay, so that was the whole idea, trying to see that, okay, can we try to, instead of going through that right hand side, we do it here with MPI for Spark, with running MVAPICH to J, MVAPICH 2. So this will provide a performance portable solution across the interconnects, and that's what we have done. So we have this project called MPI for Spark. You will hear more about that tomorrow afternoon. There is a tutorial. We have taken that native transport, going through a MPI Java binding, JNI, then we have the native MPI COM library. And now if you see, this is the very latest number, MPI for Spark with MVAPICH 4.0. We'll be making a release today. So there are 3 lines here. This is the lower is better. So the blue line and then the orange was actually our own design, in the RDMA design. Okay, but that is several years back. Now there are much more advanced things we can do with the MVAPICH 4. So that's how we are able to. And then the brown line is the standard IP over IP. Okay, that means cannot. Now the interesting thing is these are only InfiniBand based solution, but this can run. We have tried on like the slingshot. We have tried on OmniPath. This solution will directly work there. I don't have to redesign Spark, optimize Spark for slingshot, because since we are going through the API layer has that support, automatically we get the benefit. The other thing what we have done is for the Dask. Some of you might be knowing the Dask is like a new data science workload kind of things. So the standard solution has been either you go through TCP/IP or you go through the UCX. That is the right hand side we have done the Dask with MPI for Pi and MVAPICH to GDR. And here you will see like this is on the TAC Frontera on their GPU based systems. You can see again 3 bars, IP over IP, UCX and MPI for Dask. The left hand side is execution time, lower is better. Right hand side is the throughput, higher is better. So the MPI for Dask is able to give almost like a 2.9 times better performance compared to others. So then moving forward, as many of you know, even this is from the very beginning of the MVAPICH project, we have the OSU micro benchmark suite. So every time we have a new feature, we also provide the corresponding feature on the OMB, and many of you use that. It has become like almost a de facto standard. And in fact, a lot of procurement guidelines you will see people indicate like a report OMB performance. Okay, so we have, it is not like an IEEE standard, but we have almost like over the years, this has become like a de facto standard in the HPC. So gradually we, depending on the technology, depending on the features, depending on the request, we keep on enhancing. The latest one is for 7.4. Yesterday, you heard a presentation from Hari and Nat. Please take a look at this. There are a lot of new features there we have provided. The other thing, the project which I've been continuing, this is called IDAM, InfiniBand Network Analysis and Monitoring. So here the idea is that we have worked on multiple things, like working with Samir, taking some of the MPIT information, taking the job information application. So the idea is that as I'm running the job, it's like a dashboard. I can exactly find out what is happening on the network, even from a network packet level, and correlate it with the job scheduler, so that you can actually very quickly see whether your system is running properly or not. In fact, tomorrow we'll get a presentation from Mahidhar from SDSC. They have actually deployed it in a production manner, and they were able to use the INAM to really solve some big issues, performance issues on their file system. So he will be talking about that tomorrow. So this is the INAM 1.0 release. You can go to the website and you can get a lot of and then towards the end, what I would like to indicate, because we work with a lot of community, we have actually a best practice page. Some of you might have seen it. All these are different applications. As you know, to get the best application on a given system with an MPI library, you need to tune a lot of parameters. And we have done for some of these applications, and these are all included there. And we encourage the community also to contribute. If as an end user, you have seen like some parameters working well for your applications, please send it to us. We'll put it on our website with a credit to you, so that other people who are trying to run similar applications don't have to reinvent the wheel. Okay, so that is the kind of the community practice we are trying to bring. So here, one example we are trying to show, like we worked with Samir, like a GROMAX. We call it like a performance engineering with Tau. They have the Tau support. We have the MVAPICH. We have done very tight integration with the MPI tools interface, and with very simple steps, you can actually get like a 2.5x improvement for an application. Like from MPI library, we can get a lot of performance variables through MPI standard and give it to the Tau. Tau does the analysis and generates some control variables. We can give it to the MPI library, and then you will see you will get this kind of behavior. So with this, let me quickly go into some of the upcoming features. As I said, like I'll talk a little bit about Intel GPUs. So these are very initial designs which are coming out for Intel GPUs, and for the timing, these are very small scale system access we have. We don't have access to very large scale Intel GPU system, but here you can see like all reduce we have done. These are comparing to Intel MPI. We can actually deliver like a 15x kind of improvement compared to the Intel MPI. These are not available yet in the release. It will be available with the MVAPICH for RC1, but you can see this kind of performance. Even here it is like other reduction-based collectives, similarly 13x, 20x, 22x improvement. And Chen-Chun talked a little bit about this yesterday in his short talk, but these are work in progress kind of things. And there we have used actually not only just the benchmarks, we have actually tried the AI workload. So this is TensorFlow with Hoverboard. Using our new designs, as you can see, you can actually run your training applications with like a 13%, 22% benefit. Same thing also happens with PyTorch and Hoverboard. So this again shows the benefits of that converged software stack. So as soon as we take care of the benefits at the MPI layer, we are able to give it not only for the HPC application, but for AI application and big data applications. So this is also very fresh results. We have taken similar kind of designs to the AMD GPUs. These are not publicly available, but they will be available soon. So this is like a comparing with Cray MPICH, because most of the AMD systems are with a Cray, this is with Slingshot. So we are able to give like a 62%, 80% benefits. This is also with the all reduced around 33 and 56% benefit. So then moving forward, as I said, like we have started looking at the FPGAs. So there again, the very similar idea, what we have taken from GPU. If you remember the GPU direct RDMA, that project, very similar, we are trying to do FPGAs. If there are two FPGAs, can they communicate using direct communication? So we want to bring this MVAPICH FPGA. It has not come out yet. You will see coming in the near future. And Nick Contini, he will be giving a presentation on this tomorrow afternoon with more of these details. So then I talked about the CXL. As you know, CXL is coming as the next generation kind of interconnect, but it's not a replacement for the major interconnects. But the idea is that currently, if you see within the node, you have only like a 2 sockets or maximum 4 sockets. They are talking about shared memory. But you can take some of these nodes together with CXL. So you can have like a super node kind of things. Okay. So this is where the CXL is trying to put it here. These are some of the parameters that you can see, like a latency 1x to 2-3x. CXL will provide and disaggregated memory. So we have started working. In fact, we are working very closely with our ETRE collaborators here on a funded project, jointly taking a look at the CXL. So what we have done as of such, there are not many products out there, or rather we don't have real access to CXL hardware. But there are a lot of emulators are coming up. Okay, so what we have done is, now of course to do the measurement, we started with the OSU micro benchmarks, we extended to CXL. Okay, if CXL comes, how these numbers look like. So currently there is a simulator or an emulator, you can call it, called QEMU, QEMU. So we have started using that to understand the trade-off, CPU to CPU, GPU to GPU. So this is like a H to H, which is CPU, CPU, D to Ds, device to device. We just published a paper at the PERC conference, and tomorrow too we'll present more into details on this. So here we can see, at least based on the emulation, if you plug on the parameters, then you can understand and see where CXL will benefit. Okay, so that's the kind of evaluations we are doing. Then here I mentioned like a large image inferencing. This is still an unsolved problem. Quentin presented this. If you take a look at like pathology, these big images, these are like a 100,000 by pixels. These are very compute and memory intensive, and they cannot actually fit into a single GPU. So this is, we call it like a high resolution inferencing. Okay? Here we have like come up with different kinds of parallelism, quantization technique, and Quentin presented this yesterday. You can see from the talk, but here some of the results. We also presented this paper at the PERC. So here it says like a left-hand side, if you see using FP32 or FP16, we are able to get like in this kind of single GPU, 2 GPUs it cannot run, you have to go with a 4 and 8, and this is where we use the different kind of parallelism, SP and MP, to actually solve that inferencing. And finally, I would like to go into this. This project is actually Hari is taking a lead. You can talk more. So the broad idea is that can we actually have a conversational AI interface coming up and trying to like think of like a, let's say left hand side you see HPC user currently you choose an application, find out all the dependencies, install, documentation, and yesterday Samir, you showed that big chart, you know, all the dependencies kind of things. So the challenge is like, okay, can you before going to bed tell the system in a conversational AI saying, okay, run whatever like a WRF with this size on this parameter with this MPI version on this cloud, and then go to sleep. Okay, can the system automatically like build all the steps, come up with all these things? So that's what we call like a conversational AI interface, and come up with the final program and run it. Morning, you'll get a note saying, good morning, your results are there. Okay, so that is the kind of the project what we are working on. If you have any questions, please talk to Hari. Okay. So with this, let me conclude here, but I would like to indicate some of the real highlights of some of these things what we have been doing. These are all the slides, but what is the real impact on the science? So I'd like to highlight 2 of these projects. We are very proud. We work very closely, still working very closely with Lawrence Livermore National Lab. And this is one of the project 2.5 years back. Many of you would have seen NASA's DART mission. They had the complete simulation of like if an asteroid comes, how you can actually fly an aircraft and then destroy the, and all those simulations were done using MVAPICH 2 on the Livermore machine, and we were able to work very closely with them. The same thing also happened on the second, which is the nuclear fusion research. Okay, very similar things that was like done 2022, December 2022, big announcement came. And once again, we are very happy that we helped with this kind of big science applications. So these are some of the applications, and we have been working also with the Dan on many of their like attack systems and many science applications. Same thing with also Idaho National Lab. You will see some of those examples coming out. So we are trying to take the designs not only just from a small level, but really helping into very large community. So with this, this is our broad goal. This is like a converged software stack. So the MVAPICH is no longer just a HPC, but leading into the to the AI workload and the future workload. I'd like to thank all our sponsors. But last but not least, these are all the heroes. Okay. As you see, this project has been going on for 23 years. So these are all my heroes. I don't, every time I give a presentation, I indicate this, all this like almost a work of 100 people, what you are seeing. So with this, let me conclude here. If there are any quick questions, I'll be happy to take now. Otherwise, we can go for a coffee break and then come back, and we can have more further discussion. Thank you. Any quick questions from anybody? A lot of materials, but we'll link the slides to the program page, and you can take a look. Yes.
So is MVAPICH 4 Plus, will that be ABI compatible with MPIC 4 or with 3.4, or what is the ABI compatibility with MPIC?
With MPICH?
Mm-hmm.
Yeah, MVAPICH. So all the MVAPICH series is actually a derivative of MPICH. Okay. So we are ABI compatible with MPICH. Okay.
Is there any specific version compatibility?
Yeah. I think if I go back, I think the latest one is 3.43.
It's really with just MPICH 4.0. Is that?
No, I think it is the. Let me go very quickly. I think it was in the one of the slides. Just a minute. Yeah, I think the might be anybody can indicate here.
Dr. Panda, if you'd like me to take that one. So all MPICH versions are currently ABI compatible with each other. So MVAPICH has done a lot of work to not break the ABI compatibility, even as we go up in standard versions. You guys are probably getting it.
Yeah, so I think the latest version is based on, I think on the website you will see, I don't put it, I think their latest 3.43, but all MPICH and derivatives, as Nat said, they are compatible, ABI compatible, and there is a new initiative taking place. I don't know whether you know, people are trying to also bring OpenMPI derivatives and MPICH derivatives together, okay? So as soon as that is resolved, we'll be compatible across all the different libraries.
Yeah, so we will, sorry, there was echo in there. So we will continue to be ABI compatible unless the MPICH ABI compatibility changes. Right now, the MPICH ABI compatibility has not changed even as they've gone up to 4.0. And then moving forward, there is the ABI initiative within the MPI forum that is trying to make all MPI libraries ABI compatible. As we go up to the 4.0 version, we will support that interface as well. So if you choose to use that interface, we would also be ABI compatible with OpenMPI and any other MPI implementations that use that ABI compatibility layer.
Okay, so there is a question here. Do you have any plans for incorporating quantum computing in future releases of MVAPICH? This is very interesting. In fact, last semester, we started a course at OSU, Quantum Computing for HPC and AI. So we have actually some of the things in progress. So what we have done is at least the quantum simulation. So a lot of people are doing quantum simulation using MPI library. So that is our first step. You will see some papers and all coming out saying how you can use MVAPICH to actually enhance the performance of those simulations and scalability. Okay, so that will be our first step. And then the second thing is that, again, depending on like how these quantums are being deployed, we are keeping a very close eye. If there is an environment where you are trying to do, most of those systems as they are coming is like quantum computing is like an accelerator kind of things you can offload. So in that context, yes, we will be ready also to MVAPICH to offload things to the quantum systems. But once again, depending on where systems are, we'll be very happy to work with collaborators and have those kind of solutions. We don't have a quantum system here in OSU or in my lab, just to be very clear. Okay. Any other questions online or here in person? Okay. So if not, let's take a break. I know we are running a little bit late, so might we take a break up to 11? We'll delay it by 15 minutes and we'll recover during the lunch time. Okay. So we'll, after the break, we'll start with Rich at 11. Okay. Thank you.